Thank you all so much for coming. We're so glad to have you all here today to celebrate Carl Sagan's 91st birthday with a special lecture from Gillis Lowry. So, for those of you who do not know her, Gillis is a former president of CAS, research assistant for the Carl Sagan Institute, and current master's student at San Francisco State University. So, most of her work focuses on exoplanetary science and science communication, and she won second place in the annual Griffith Observatory Science Writing Contest. We are all so very excited to have her back in town, so without further ado, please welcome Gillis.
Thank you all for having me and for helping me celebrate Carl Sagan's 91st birthday. Once I get the mouse back over to my screen. There we go. All right. So some of you in this room perhaps are not familiar with Carl Sagan. Maybe you saw the free apple pie advertisement and decided to show up without knowing any other information, and that's all right. So I'm going to give you a short version and then a long version of who Carl Sagan is. Then I'll start to get into some of my own research, and finally I'll conclude with a little bit of explanation of science literacy. I'll get into a lot more of that later. But for now, the short version: who is Carl Sagan? Red turtleneck wearer, as you can see, but also an astrophysicist and a science communicator. In the 1970s and 80s is when he rose to popularity. And he was one of the first really big science communicators who was a scientist that everybody knew about pretty much on their TVs, in their homes. He was sort of the science guy. So we'll get into the long version in just a moment. But if you remember the title of this talk, it is The Search for Intelligent Life on Earth, which is maybe a little bit of a jab. It's up to you to decide whether that's a fair or an unfair jab. But it is not an original title. In fact, Carl Sagan has used very similar titles and jokes before, so have to give him credit for this one. In these, a lot of times he was referring to his research in looking back at Earth and trying to detect humans on Earth, to use that as an example for finding aliens. But it does also beg the question about how intelligent life really is here on Earth. So before I give you the long version of who Carl Sagan is, why listen to me at all? Carl Sagan died in 1996, and after all, in 1996, I was -5 years old. So even though I did not overlap my lifespan with Carl Sagan's at all, I was born 62 years to the day that he was born, and ever since I was a young kid, looked up to him. When I first found out that we shared a birthday, I was like, neat, I enjoy science, I enjoy writing. He did both of those things. And as I started to get older, I started to look into more and more of his work and realized it was something that I wanted to do too. So I have followed down a similar path of research as he did, at least in the few years that I've been doing research. And I have also prepared for this presentation by reading various biographies of Carl Sagan, and in reading his book, The Demon-Haunted World, Science as a Candle in the Dark, which is what largely the last part of this lecture about science literacy is going to be drawn from, as well as modern research in science communication and literacy that I have explored. So, the long version. Who was Carl Sagan? Many people know him by his famous book and television show Cosmos in the year 1980, and for a decade, it was the most watched series on American public television. So it made a huge impact, and of course, beyond America as well. It was a global sensation. And one of the things he talked about in a lot of his science communication, many of his books, was human history in the context of the cosmos. So he wasn't just interested in studying space. He was also interested in putting us in that context. And he often used the framework of great demotions. So he would say that for much of human history, when we looked up at the stars, and maybe you'll do so at Fuertes Observatory later tonight, more likely you'll be looking at clouds. But if you look at those clouds and pretend you're looking at the stars that our ancestors thousands of years ago across the world saw when they looked up, then you would start to get a sense, if you watched over many, many hours, that these stars are moving overhead, If you went out many, many months, you would start to see the movement of the planets and the moon. And in all of that, you probably wouldn't come to the conclusion that that the Earth is going around the sun, that the sun is going around the center of a big Milky Way galaxy, and that the Milky Way galaxy itself is just one of many, many galaxies in the universe. So the first great demotion was to realize that not everything goes around the Earth. And that was just because we started to get better and better data, and so we came up with a new scientific model to be the standard. After we realized that the Earth was not the center of everything, we thought, well, maybe the sun is the center of everything. We're close to the sun, which is very big, so that's pretty special. But the sun is just one of many solar systems in the galaxy. Then we started to realize the galaxy itself is one of many, many galaxies, and all of that is expanding out into space, a vastness that we can't even comprehend. The next big demotion, perhaps, is to discover that we are not the only creatures, intelligent creatures in the universe, that there might be other ones out there on other planets. And this is a question that Carl Sagan devoted much of his career to. So some people have the impression that Carl Sagan was all talk and no science, but he did a lot of science. He was very well known for a lot of science on habitability. He studied for his doctoral dissertation whether life could exist on the moon, Jupiter, and Venus, which nowadays we sort of take it as a given that there's probably not life on the moon, has no atmosphere. There's probably not life on Venus because, as Carl Sagan came to discover, one of the people discovered that Venus is very, very hot. It has the runaway greenhouse effect that traps heat under lots and lots of gas, and that means that the surface of Venus is so hot that any spacecraft we've ever sent there has melted on the order of hours. So probably not a place where there's life. But he continued to look. He looked at Jupiter and developed a theoretical system, an ecosystem of sinkers, floaters, and hunters. And he started to look at the moon Titan around Saturn and see that there are molecules there that are made up of organic stuff, basically the ingredients that you can put in to get life, but not life itself. And he was part of many spacecraft missions in his career that again and again showed him that there was probably not life on these planets. The Mariner missions to Venus and Mars, and the Viking mission to Mars that slowly revealed these places were kind of barren rocks, at least as far as we knew then. So there were other things he also turned his attention to, not just within the solar system. He sent many messages and received radio data at Arecibo, which was a radio telescope operated by Cornell for many, many years. Rest in peace. And along with Frank Drake, another Cornell professor, they sent the Arecibo message, which is a little pictogram here of a little guy, radio wave. They sent it toward a star cluster, not really because there necessarily was life there, but just as a sort of proof of concept to say, we can send messages out into space with an alien audience, and to ask the question, who might be receiving those? And he asked that question again and again with the Pioneer plaques on the Pioneer spacecraft, and then with the Voyager Golden Record. So before I get into the Golden Record, Voyager was another mission that he was part of that went to the outer solar system, took pictures of many of these worlds for the first time, and on it, it carried a golden record with 27 songs, greetings in 55 languages, all sorts of stuff that he and his team hoped that we would want to represent ourselves out in space if an alien were ever to find it. Not any mentions of war, didn't want to send a potential threat to aliens. But even if the chances of finding this are astronomically low for any aliens, it's a tiny spacecraft and space is really vast. It starts to ask the question, how do we want to present ourselves and what kind of species even are we? Near the end of his career, Voyager turned its cameras back towards Earth. And this was the result of him asking for a decade of NASA that after all the pictures were taken, they turn the camera back and take just one last portrait of the Earth. Not for any scientific reason necessarily, but to show that the Earth is a tiny speck in the enveloping cosmic dark. And here you see it suspended in a sunbeam. If you don't see it, I'll make it a little clearer. with a big arrow for you because it is basically 1 pixel at this distance. And this is still within the solar system. The Voyagers are still traveling. Some may say they've started to leave the solar system. There's different boundaries of what you consider the edge. And this week, actually, they will reach 1 light day away, which is a big deal. That means it takes light only 1 day to travel all that space to reach us. And in a moment, I'm going to tell you how far the other stars are to put that into perspective. But he got this portrait of the Earth to help us consider what our world might look like from afar. Would we see any intelligent life from this distance? And this is still a much better picture than we can currently get right now of any small planets that might be like ours. So Carl Sagan died on December 20th, 1996, at the age of 62. And at that time, we had only discovered around 8 planets that orbit other stars, exoplanets. This was the very beginning of a field that I and many people have joined over the past few decades that allows us to ask that question of whether there's life on other planets. But he died just at the very start of this field. Now we know that there are over 6,000 planets we've discovered so far. But if you look at any star in the night sky, chances are you're looking at least 1 planet around every one of those stars. And if there's 100 billion stars in the Milky Way alone, that means there's at least 100 billion planets, we think. And chances are that roughly 1 in 5, maybe, of those could be rocky. And then we start to ask the question, well, if it's rocky and it has a surface like the Earth, then what sort of stuff could be on its surface? And that depends on how close it is to its star. If it's too close, any helpful material for life, like water, would boil away. If it's too far, it would freeze. But if it's in that right distance from its star, the habitable zone, then it might have liquid water. And maybe there's life out there that doesn't need liquid water, but all we've got is the example on Earth. So if we've got water, we have energy from the star, maybe there could be life on that planet. So I have started to ask that question in my own research at the Carl Sagan Institute, and even now that I've gone on to my master's program at San Francisco State. And my research has been to look at all the planets we've found so far, which is around 6,000 of them, and start to narrow down that number into just the habitable zone ones and the ones that could potentially be rocky. So in a moment, you're going to see, there we go, 6,000 planets we've discovered so far, about. And once you narrow down the numbers to just the habitable zone ones, you're down to just a few hundred of them. And after you've got those few hundred, you're going to be looking at, after that, just a few dozen planets. And then you've really got a pretty small number that might have life on them. It's a manageable number so far. Maybe in the future, once we start to get up to 100 billion, it's going to be a lot harder to look at each of those cases. But the Carl Sagan Institute here at Cornell is continuing Carl Sagan's legacy, extending that out into exoplanets. And just like he did, using the example of looking at the Earth from afar to see what we might be able to, what sort of data we might be able to get from these planets if they have similar life to what we have on Earth. So we have researchers who are looking at microbes on Earth, seeing what sort of reflected light comes off of them, because that's the kind of light we might be able to receive in our telescopes. And we have people who are looking at the Earth over time. So this one's talking about alien dinosaurs, because during the time of the dinosaurs on Earth, there's actually higher levels of oxygen, for example, these sort of biosignatures, types of molecules in the atmosphere that we might be looking for with our telescopes. Because if you have a certain number, a certain type of molecule, maybe not just oxygen, but a certain combination of molecules that are just too hard to explain by any other means than life constantly putting them into the atmosphere, then that would be pretty compelling evidence. So my research specifically has been to look at all those exoplanets, like I said, narrow them down. This is around 40 of the planets that are within the habitable zone and that are small enough to be a rocky planet like Earth instead of becoming a gas giant like Jupiter. You'll see they range of what host star they're around. So from the bottom of the plot, We have red dwarf stars, which are very small and a lot cooler than hotter stars at the top, like our sun. And then on the x-axis, from left to right, we have the starlight that the planet receives. So this is basically how much energy is it receiving from its star. And you'll see the boundaries of the habitable zone here are kind of curvy. And that's because you're getting a different type of energy from your star. If you're around a cooler star, a redder star, you are getting redder colors and going into the infrared more than our sun emits. And then around our sun, you're getting to higher energy, to ultraviolet light. So that's going to do a lot of different things to your atmosphere. It's going to interact with the molecules in different ways. So for that reason, these boundaries are a little hazy. And then you'll see there's the optimistic and conservative habitable zone because at the moment we're kind of making our best guess. We're using the example of Earth and we're using the example of Mars and Venus to say we know by the time you get basically as close as Venus, you're not going to be habitable. By the time you get basically where Mars is, you're not going to be habitable either. So we know it's got to be somewhere in that range, but you can make different estimates. And until we actually study these planets, we're not going to be able to tell where the true boundaries of a habitable zone lie. So the issue, because it seemed like, oh, we got 40 planets to study. That's a good number, right? But all of these rocky planets are really small. The Earth might seem big to you if you're a human being, but if you're an exoplanet scientist in addition to a human being, these planets are really small. They're not gas giants like Jupiter. So the contrast between them and their star is pretty high. They are very, very small compared to their stars, which are very, very bright and sort of wash out our telescopes. And all planets are far away. I said earlier I was going to tell you about how far away other stars are, how far away other planets are. If the Voyager spacecraft, which are around 1 light day away, are the farthest we've ever sent anything, well, the nearest star is 4 light years away. And that's the nearest one. So some of those planets I was showing you before are hundreds of light years away, which makes it really difficult to observe them. How do we observe them, though? So normally we see the planet passing in front of its star. And as it does so, we see a little bit of a dip in the starlight. There's a little bit less light getting to us when that tiny circle is blocking it out. So this is the sun and the Earth. You can see how small the Earth is compared to the sun. And it's just that tiny little bit. It looks kind of like some of the star spots, the other spots you saw in the sun. So it can be very hard to figure out what's really a planet. And then if you also want to figure out what the composition of the atmosphere of these planets are, that's even trickier than detecting it. As you can see here, this planet, we'll call it the Earth. It's pretty small, and it has an even tinier atmosphere. What I've drawn here is much bigger than the atmosphere of the Earth would appear. It's just a tiny skin along the edge of the planet. But some of the light from that star just happens to pass through that atmosphere, and as it does so, the molecules in the atmosphere interact with the light, and they absorb some of the colors, some of the wavelengths of light, so that when that starlight reaches our telescope, we see sort of chunks that have been taken out of it, dark spots that have been taken out. So using that, because we know that every molecule, every element takes out different colors, we're able to figure out, based on which colors are missing, what molecules are in that atmosphere. But this is a very tricky process. Again, the star is really bright, and to disentangle all of that from the starlight is really difficult. So, with all that being said, the only planets we've really had a great shot at, and not even great, an okay-ish shot at so far, have been the TRAPPIST-1 planets. So if you've ever heard about the TRAPPIST-1 system, there's a pretty good reason for that. It's because that's pretty much all we have a shot at so far with our current capabilities. Why is that? You'll see TRAPPIST-1, all 4 of these planets, which are given the very creative names of D, E, F, G, are very low down here. They have a very small star. So if you're a small planet, but you're going around a smaller star, you're going to block out more of that light than you would of a big star. So for that reason, these are some of the best candidates we have so far. But if they're going around a really small star and it's not putting out a lot of energy, as much energy as the sun is, that means you're going to have to be very close in to your star in order to receive the same amount of energy. So these little magenta dots going around in that green habitable zone are all of the TRAPPIST-1 planets. And they are much closer in, as you can see, than the orbit of Mercury in our system. But because the star is so much smaller and has so much less energy than the sun, that means they're in the habitable zone. Their days may be only 5, or their years may be only 5 days or 20 days long, but they're in that sweet spot that they might have liquid water. So we think. We still have to continue to observe them before we can come to those conclusions. So the step before you observe is to try to come up with what you think you're going to observe, and try to come up with models so that once you do observe, you'll be able to compare them to the models that you've already run. So some of the things that I've been doing, after I narrowed down all those planets into just the habitable ones, I started to look at the best candidates, mostly TRAPPIST, and started to simulate the data that we would get from the James Webb Space Telescope. So this is the simulated raw data from TRAPPIST-1e, and that planet we think is sort of the closest to receiving the same amount of energy as Earth. So the y-axis here is the amount of starlight that gets blocked. So you'll see there's a tiny bit more starlight getting blocked up here than down here. But eventually, we're going to simplify that out and start to see the little wiggles that would be the colors taken out of those from those molecules in the atmosphere, we hope. So this is the raw data. It looks pretty, I have to say, it looks kind of terrible. I don't see anything really going on here except that the error bars get really big at the edges. That's just the edge of the instrument's range, though. So once we start to run some software that can actually simplify this down for us, take away a lot of the noise, and once we start to observe these planets multiple times, that'll start to make those error bars go down. And now we start to see the squiggles. So I've labeled some regions where if you saw that light being taken out, you see there's more starlight blocked the higher up it is. If you see it taken out in those regions, we know that's the signature for water. It always takes things out in that region. That's CO2, that's methane. So this would be a really great result to get if you got this with the James Webb Space Telescope, because you're actually able to fit a model to it and see what molecules are in there. Unfortunately, it doesn't always turn out as clean as this. And also, I know what molecules I was simulating here. So I'm able to then tell the computer, okay, take this data that I've simulated and fit these molecules and see if they're there. And it's able to do that because I already knew what the answer was. In real life, we're not going to know what the answer is. We're going to have to go through multiple hypotheses, test different molecules to see what fits the data the best. Unfortunately, there's not really an algorithm that can go through every molecule ever invented in the world and tell you which ones are the ones in your data. So for now, there's still a little bias in there when you try to test different models to see which ones are the best fit. But it's a start, and we've certainly gotten a start with this planet because just a month ago, this was released. The James Webb Space Telescope data for TRAPPIST-1e, the same planet that I just simulated. But you'll notice they don't really have a very nice squiggly model that's fitting it. So again, this, as in reality, it's not always as clean as we would hope it to be. You'll also notice, if you're able to read those captions, otherwise I'll read it for you, there's an atmosphere model and a no atmosphere model. So we're not even getting into the details yet of, is there CO2, is there methane? At this point, we're still trying to figure out if there's an atmosphere at all. So we're just beginning with these planets. But as our technology gets better and better, hopefully we'll start to get smaller and smaller error bars, and we'll start to be able to consider what specific molecules are in the atmosphere. So this is just a little meme I made. Yeah, I think sometimes people get the impression that it's easier than it is to see these planets. If we can know that they're there, then we should be able to figure out what they're made of. But it's really, really hard to figure out even that they're there. We're not even close to taking pictures of these planets yet. So it's very, very hard to find signs of life on these planets. So what's the best way to keep doing this? Build bigger telescopes is a great one. There are a lot of upcoming ones. The Habitable Worlds Observatory is one that many scientists are very excited about because that's the explicit goal of it, is to search for life on other worlds. And we've also got some good ground-based telescopes that are going to start searching. And hopefully, as I alluded to before, we're going to start to be able to take pictures of these planets. This is an example of pictures we can currently get of gas giant exoplanets. So these are way bigger. These are like Jupiter, at least size planets. And they're typically very young planets, so they're also still very hot. And that means that it's a little bit easier to see them next to their super hot, bright star. But I think it's really neat that we can get these videos actually of planets orbiting around other stars. And hopefully we'll start to get that sort of thing for smaller worlds soon. So that has been the search for life on exoplanets, at least for any sort of life that's leaving a signature in the atmosphere of that planet. But I think it would be simplifying a bit too much if I didn't also talk about the search for intelligent life through radio, because that's also something Carl Sagan did, as I said, with the Arecibo telescope. So maybe we've had a little bit more success here than we have with exoplanets. This, perhaps, is a signal of an intelligent civilization. You can see that this is when they were pointing at the source. This is when they weren't pointing at the source. And then they pointed at it again. They saw the signal again, this slanted line. So that seems like pretty compelling evidence. But this is actually, it is something that's outside of our solar system, but it is Voyager again. So we have found intelligent life somewhere slightly outside our solar system, one light day away. So we're able to do it. So this is another example of using our own technology, the signals that we would receive if we were aliens looking for us. And if we start to analyze those and know what those look like, it might help us find aliens that might have a Voyager spacecraft of their own. So we'll keep building bigger telescopes and building bigger radio telescopes. We'll start building modeling software to maybe be able to fit more of those molecules some more. We'll build the next generation of researchers, which the Carl Sagan Institute and its director, Lisa Kaltenegger, does a great job of here at Cornell. And ideally, we would also keep funding NASA as an unbiased source of science. And there will be some ways that you can help out with that later in the talk. There will be a QR code at the end if you'd like to scan that, so stay tuned for that. But for now, what happens if we do find alien life? What are we going to do then? How do we announce this to the world? It has been announced to the world already. Not really in an ideal way. So this was earlier April of this year. There was an announcement by a scientific team studying the exoplanet K218b that they had found the most compelling evidence for life yet on another planet. But once you start to talk to other scientists, they say, let's be a little more skeptical about this. This is not quite the level of significance that we would want. The data is still noisy. So this is not something we would call a detection yet. But of course, if you start to say that you've detected significant evidence for life, people will run with that, as people always will. So maybe the question is less of just how to announce aliens. Maybe this is a broader systemic issue, and we should really be asking, what is the best way to prepare our society to think critically about scientific conclusions, and not just about aliens? There's lots of scientific conclusions that impact our lives day to day. How do we deal with that? And ideally, I mean, we have this really lofty concept of critical thinking, and we would all love for everybody to think really critically all the time, just focus on everything they ever see, analyze every source all the time, do their own independent research. And hopefully you would have a certain level of scientific literacy when you're looking at these things, but what do either of these things really mean? It's kind of, you can just point to it and say, let's do it, and never really define it, and that doesn't really help anyone. But this is something Carl Sagan talked a lot about and did give some concrete solutions for in his book, The Demon Haunted World. And This book also has some passages in it that have been floating around a lot recently on the internet. People like to say he's predicted 2016, he's predicted 2020, he's predicted 2025. Um, and in a way, he has, but I think these are things that were coming for a long time that many people could see. He's not the only one. But I'll go ahead and read you the passage and see what you think about that. I have a foreboding of an America in my children's or grandchildren's time, when the United States is a service and information economy, when nearly all the key manufacturing industries have slipped away to other countries, when awesome technological powers are in the hands of a very few, no one representing the public interest can even grasp the issues, when the people have lost the ability to set their own agendas or knowledgeably question those in authority, when, clutching our crystals and nervously consulting our horoscopes, our critical faculties in decline, unable to distinguish between what feels good and what's true, we slide, almost unnoticing, back into superstition and darkness. So yeah, if you've been having a rough few years recently, that's probably resonating with you. But like I said, there are things we can do, and this is something that people could have seen coming for a long time. It's not just 2016. Humans like to believe what they want to believe, but there are things we can do about it. So what exactly is science literacy? So we can start to do something about this. It's not just memorization. It's not just knowing a scientific fact. There are some studies out there by the Pew Research Center that say a certain really high number of Americans don't know that the Earth goes around the sun, which is concerning, but it's not the only thing, hopefully, that you're learning from your science classes. If you only ever come out of your science classes knowing the Earth goes around the sun, F equals ma, all of these things, then you're not really going to be able to critically analyze science and try to determine the validity of scientific conclusions. So there's a lot of different steps in the process of science. You want to know how people conduct experiments and why certain methods are better than others. You probably want to know about the concept of control groups so that you're not just testing something without testing it against a group that wasn't affected. You want to be able to evaluate probability, know what it means when someone says 1 in 4 of your children might inherit this disease from you. You want to know what that means so you can analyze the risk and make decisions. You want to know about error and uncertainty in science so that you can start to say, like, we know that this is a big claim, but maybe it's being misrepresented because we know there's a certain level of uncertainty in science all the time. You want to be able to know about large numbers, about the difference between a million and a billion and a trillion. They're really quite different things. And you want to be able to read basic graphs and also to identify the biases in these graphs. For example, you want to know when people are trying to bamboozle you by making the graph misleading. And there's a whole lot more that I can't go into right now, but I'll have some resources at the end that start to delve into this a little bit more. So hopefully these things will start to give you a sense of how science is conducted so you can start to analyze what you hear about science and try to figure out if certain science conclusion is valid or not. Maybe it'll also give you a sense of the beauty of the natural world, but we're going to consider that a stretch goal for now. Maybe after we help with the state of our democracy, we can start to see how people are affected by this. No, but really, I think there is a lot of value in the natural world that just comes out of learning about science and viewing it as a meaningful endeavor, as a way to gain knowledge and to learn about the natural worlds and not just to memorize scientific facts. So, as an example, to quiz yourselves a little bit, what do you even think it means to study something scientifically? You don't have to answer the question to me personally, because there's no shame in not being able to come up with an answer. But if you think about it, then maybe you'll start to come up with some of the things you were hopefully taught in school about conducting experiments, how to construct an experiment, constructing hypotheses, not just making up one hypothesis or one explanation after you've looked at the data, but coming up with multiple explanations so that you're not just choosing the one that you want to believe. So if you thought about any of these things, it's fine. But it's not just a list of things, it's more of a way of thinking as well. So realizing that you have to form hypotheses, but also realizing that there are certain safeguards in place already in the scientific process in order to get published. Things like peer review. These are things that in any well-trusted journal are things that are already going on. Ideally, once you know these science literacy skills, you would start to apply them in your life as well. But as research has shown, just knowing something doesn't necessarily mean you're then going to do it. It depends on a lot of factors, especially the environment that you're in and the identity that you hold and how a particular issue ties into the way you've already constructed your identity. But if you help start to build communities that really value science, such as the Cornell Astronomical Society, then hopefully that will start to enforce some of these scientific literacy skills, not just in a knowing way, but in an actual conducting them way. So I don't want to shy away from the big elephants in the room in these topics because Carl Sagan didn't do that either. He spent much of his career trying to promote knowledge of the climate crisis. He testified before Congress repeatedly. He protested at nuclear test sites, and he wouldn't want us to ignore it either. So these are some interviews that the Pew Research Center conducted that I found were very interesting. Both of these people, two separate people, they say that they have a lot of respect for scientists. And they say that they're willing to listen to scientists. I can't analyze their behavior to know this for sure, but the fact that they're open to the idea is a positive. And then they go on to mention that statistics can be changed, science can be written to have the results that you want, and that you're going to be biased based on who's funding your research, which is not an incorrect conclusion to make necessarily. People are biased, and if someone is funding your research, you probably are biased. But not all science is biased. Not all journal is funded by a particular interest group. Any well-trusted journal is not. So these interviews go to show that not everybody who doesn't believe in climate change is completely rejecting all scientists as people and as a pursuit. Only 2 of the 32 people they interviewed here actually said that climate change is a hoax, it's a joke, I'm never going to believe in it. The other 30 said things that are sort of similar to this. So this means that people, maybe if they know a scientist or if they start to learn more about the process, why there are safeguards in place to prevent these things, that it is possible for people to come around on these issues potentially. But again, a lot of it still has to do with people's identities and what communities they're in. And it also has to do with how many barriers there are to them understanding science. So many scientists say, and in a study of life science professors at Cornell, researchers at Cornell, around 75% of them said they feel like it's their duty to communicate these things. But not all scientists necessarily have the support to communicate science to the public more than they already do. So that's one way things could be changed, just to start to have more of an interface between scientists and the public, because they want to do this. So removing a barrier in that sense, and of course, removing educational barriers to start to make science more approachable to people. And to also frame science, not as a memorization of facts, but as a way to find meaning in the world, hopefully tying into that finding beauty in the natural world. If you start to frame it as a story, which it is, it's a story of the great demotions of humanity over time. It's a story of looking up at the stars and seeing what patterns you can make out of these things, what models you can make out of the world. If you start to frame it that way, I think people might be a little more inclined to learn about science and to be interested in the world around them. And this is from a study I should mention by Bruce Lewinstein, who is also a Carl Sagan Institute researcher. So we also have people in the Carl Sagan Institute who are researching things beyond astronomy topics, engineering, and how to communicate science to the public. So Carl Sagan did have a few extra things that he would probably want you to know about analyzing media in a scientific way. So in his book, The Demon Haunted World, he came up with the baloney detection kit, which are a few strategies you can use when you're analyzing things to determine how valid they are. So a few of them, and there's a lot more that will also be linked at the end of this presentation, but a few of them are that facts should be checked by an independent source. You shouldn't just trust the person who might be biased, and you shouldn't automatically trust authority just because they're an authority figure. You should, as I said, create multiple hypotheses instead of just the one that you want to believe. You should try to check out the numbers on claims that people have, and sometimes the simplest explanation of something really is the correct one. So Carl Sagan wasn't just a scientist and a science communicator, but he was a citizen of Earth. As his wife Andrianne said very eloquently last year at his 90th birthday celebration, he wanted to promote democracy. He did promote democracy. He went to naturalization ceremonies for new citizens to tell them about science. He protested at nuclear test sites. He was a citizen of Earth and wanted us all to consider ourselves to be citizens of Earth. So, a final thing I'd like to close out with, a bit more of my personal connection to Carl Sagan. Every year around the time of my and his birthday, I go back to his grave. I look at all the trinkets and the tributes that people have left him. And a lot of times I leave a letter sort of talking about the state of the world and how that's been affecting all of us recently. So to close out, I'd like to read a little excerpt from the one I left last year. The letter I might leave this year is yet to be written. We'll find out soon. But a lot of the things I wrote last year are unfortunately still very true. So I wrote that the first time I left a letter here nearly 7 years ago, I had hoped it could be quick. We could claw our way back up the slide of superstition and darkness. There will come a breaking point in all this, for better and worse, and either way, it will remain a constant fight to come close to peace, then to maintain a society where truth feels good, where kindness feels good. I still believe that you were right to see the good in human nature. And I believe that at our core, almost all of us just want purpose, to make meaning in the world. We want ourselves to mean something. Until the very last, I want to keep in sight the purpose and love in every step of the cycle, however dark it gets. As flimsy as all of our candles in the dark can feel. But I found bright fire here in Ithaca, and I'll find it again and again. I'll keep doing my part and waving to all the lights I see throughout the country and the world. I'll be back to visit this November with all the light of the friends that I've made here. And I'll be learning as much about the worlds we wish you could have seen. Who knows? Maybe by the time I leave one of these letters in the future, we'll have found life out there for real. That won't save us from ourselves, but we'll still be saving each other. We'll be saving each other as you did for us. Thank you.
Thank you all so much for coming, and thank you, Gillis. So now is the time for any questions anyone might have. For those of you who are on the Zoom call, I have enabled chat, so you can ask them there. For those of you here, I know there are many of you here, so if you do have any questions, if you could please raise your hand so I could run the microphone over to you, that would be great. And if anyone has any questions, raise your hand high, because there are quite a lot of people here. Okay, let me come over this way.
Hi. Um, I don't know how much you would know about the sun on top of your head, but like with like TRAPPIST like being like a smaller star and like the planets being like closer to it, like how big would it roughly like look in the sky if you were like standing on them?
Okay. Yeah, that's a good question. I don't know the exact numbers, but the other planets would look pretty big. Again, I don't know the exact numbers, but the moon is pretty big in our sky, and it's pretty close to us. So I think the other planets would be pretty visible in your sky, and your star would probably be a lot bigger. But again, I'd have to do the actual math to figure out, like, diameter of TRAPPIST-1, diameter of the sun, distance, and all of that. But I would wager a guess that it would be bigger. And it would be red. So you'd be living in a very different environment with different colors. Your eyes would be adapted to more red and infrared light rather than visible. And infrared light interacts with things in different ways. The water would look different. Basically, everything would look different because of how it interacts with molecules differently.
Anyone else? Yes, let me run over.
Hello. It was a
Hello.
really great talk, by the way. Can you talk a little bit more about the research that you were working on here?
In what way?
Oh, I just wanted you to just to expand on it, just because I think it's really cool. So I think
Thank you. I also think your research is very cool.
That's so awesome.
Maybe perhaps because we did some of that research together.
Oh, I don't know about that one.
Yeah, I would not. Yeah, I wouldn't even think about that. Yeah, sure. So recently I've been doing more of that atmospheric retrieval work, and I've started to do some more work with gas giants as well, because as I've alluded to many times in the talk, small planets, very hard, bigger planets, a little easier. So I've started to look at more of those gas giants where you can actually get the squiggles of the different molecules a lot easier. So I've run models that will fit those atmospheres and can actually tell you with a bit more certainty what sort of molecules are in there. I've also done a lot of science communication here. I help run the social media pages for the Carl Sagan Institute. And for many years, one of these years it'll get done, but I've been working on a visualization of exoplanets across the night sky, so then you can click on them. Just like all those little dots you saw earlier in the presentation, that's sort of the prototype. So in the future, you should be able to click on any of those little green dots and it'll tell you all the information about that planet that we know so far. So those are some things that maybe in the future you'll start to see, and maybe you'll start to see my first published paper with Abby here very soon in the next few months. If you are the kind of person who reads the daily digest of exoplanet papers, then you might see it.
Anybody else? Yes. Oh, I will come over there first and then.
Yeah, so relating to the New York Times article about the detection that maybe some scientists said wasn't a detection, what exactly was the finding that they found, and what is the promise in that? And has there been any recent updates on that to see if it will turn out to be a possible detection or a real sign that life could be there?
Mm-hmm. Yeah, so they specifically were looking at dimethyl sulfide and dimethyl disulfide. So these are molecules that are produced by phytoplankton on Earth when they're photosynthesizing plankton. So that already is a big thing because this means that we're looking at a molecule that has to be produced by a lot of plankton in order for it to be visible in the signal. So there must be a lot of plankton on this planet. Is that realistic? Hard to say. But then there's also some things about the statistical methods that they used. In science, a lot of times in exoplanet science, we say that, and in many other sciences, we use a certain, we say sigma, which you don't need to know too much about it, but it's like the measure of how much error there is. And so they're saying their measurements around 3 sigma. We normally have to get to 5 sigma before we even say it's close to a detection, which is like a fraction of a percent uncertainty, basically. So we're just, at that point, you're like, it fits the model so well that the chance of this being a false positive are extremely low, and now we can start to say detection, but it's still kind of a charged word to say that you've detected something, because you got to have a lot of evidence for that. And you have to also have gone through and say there's no other way that this could be explained, whereas with these molecules that they were claiming, there are other ways to produce them that aren't just life. So hopefully on a planet in the future, once we start to say things like this might be a tentative detection, hopefully they will have found multiple molecules that sort of all in tandem make it seem like the chances of this not being life are very low.
Oh, I was.
Yeah, I think Bill Clinton announced that they found life on Mars in his presidency. They found a photo of something that could have been.
Yeah, a face on Mars. There was a famous picture of a face.
No, not the face. They
Okay.
found what looked like bacteria on Mars.
Okay.
But it could have also been formed by geologic processes. So
Yeah, and there are also some stirrings recently about maybe some findings on Mars now.
yeah,
So
there's going to be ones in the
Yeah.
future too that are.
yeah, so we'll see. We'll see what holds up over a long time.
Okay, I saw a question over here. Okay, let me come over there. Thank you, guys.
Yeah, so I was curious, what kind of efforts have there been to look for signs of life on non-rocky planets, assuming that there are ways for life to form on non-rocky planets?
Yeah, I'm not super familiar with other efforts. We have mostly, as far as I can tell, we have mostly focused our efforts on the small rocky planets because you have to sort of stretch your imagination a lot more in order to come up with an ecosystem that could have fully formed on a gas giant. So way earlier, I talked about Carl Sagan had a ecosystem he came up with for Jupiter, with the sinkers, floaters, and hunters. But that sort of also begs the question, we have, flying life and life in our atmosphere and all that, but we think a lot of life all of life really originally came from the ocean and from a much more stable environment. So I think people have proposed possible ways there could be life on these planets, but it's still really hard to say, like, what stable place would it have formed on? There's also the fact that there are many moons that go around gas giants that could have life on them, even within our own solar system. Moons like Enceladus and Europa that have really large oceans that are deeper than all the oceans on Earth. There could be life swimming down there, we don't know yet. But it's much harder to detect an exomoon that's even smaller than a rocky planet. So it's mostly still a realm of we need to get better data first.
Okay, we have a question in the Zoom that says, Happy birthday, Gillis, and to Carl
Thanks.
Sagan, of course. Could you talk a little more about what it is like to write and publish a paper / how peer review works?
Okay. Well, the first thing I would say is it takes a long time. Whatever estimate you had, it will take about 5 times as long, at least, for it to happen, especially if it's your first time, which it is for me. So the process of writing the paper itself is long enough. The process of going over your data over and over again, just checking everything to make sure you didn't do anything wrong, and then realizing sometimes you did something wrong, so you have to go back and run everything again. But that's all part of the process. And then you get to the peer review stage, and they send you a round of like 20, 25 comments. You respond to all the comments. You get it back, and they say, here's some more, here's 20 more comments, and you respond to all those, and then you are where I am, where you are waiting for the paper to be formally accepted and then published. So that whole process, I originally submitted the paper in January of this year, and we resubmitted the second round of comments a few weeks ago. So it has taken many, many months for us to go through and be really meticulous with this and update the data as well with new figures and all the new planets we found, had to run everything again, that sort of thing. So it is quite a long process. It's not the exact same process at every journal. And I can't say it's always perfect or anything because nothing humans really ever do is going to be 100% perfect. But it is a time-consuming process for a very good reason.
Okay, we have another in the chat. Gwyneth says, Hi, Gillis. Great to tune in from NYC. Wonderful talk. Thank you for the depth that you bring to your discussion of these key issues. The question is, if you had the opportunity to ask one question of Carl, what would it be?
Well, I already know he would be excited about all the things, so I can't be like, are you excited? I feel like it wouldn't be a question. It would just be like, look at all this cool stuff. And then we would be like, this is really cool. And that would be the whole thing. Because I don't know. He had such great enthusiasm for everything. And I would just love to hear, I guess the question could be, what do you think about this? And just hear him talk about all the discoveries that we've made in exoplanet science. But I would need like 20 days at least to talk to him and tell him everything. But that would be my question.
All right, anyone else? Oh, yes, I'm gonna run over here first.
Thanks. This is great.
Thank
Are
you.
you familiar with any of like the capabilities of future telescopes that are being built right now, and what they can do for your research?
Yeah, I'm not super familiar with the exact numbers. The Habitable Worlds Observatory is going to be a really cool one. It's not going to look at the planets that we already have on that graph, the 40 planets, but it's going to look at other systems and try to detect these planets and then hopefully to figure out what the composition of them are. So that's going to be really cool because it's going to add, hopefully, add a whole bunch more planets to that list. And I'm excited for that because then it means we won't just have TRAPPIST-1, as fun as TRAPPIST-1 is, we won't just have TRAPPIST-1 and like one other thing that maybe if you get like 100 hours of telescope time, which never happens, you would be able to observe. So I'm excited for there to be more telescopes with better capabilities and just more telescopes to give people more time to submit proposals to. And I'm excited for hopefully a big growth of new planets to look at.
Okay, I saw one over here.
Hi, thank you for the talk. Um, my question is, if you were to like try to like use the same methods on gas planets to like detect elements and stuff like that, would that still work?
Yeah, it is basically the exact same process. So normally you get the data in, you run your models of the molecules, you just tell it to put in different molecules because we know at least a little bit about the composition of these planets. They're going to have more hydrogen, for example, in a gas giant than we do on Earth. So if you know a little bit about the different types of molecules, you can start to put in different ones, but you can still use the same programs to do the same model fitting.
Anybody else? Yes.
Thank you. Great talk, Gillis.
Thank you.
So since I get to ask the last question, like I'll ask you an open-ended one that I'm
Okay.
not sure there's any answer to.
The
But
best kind.
something that I'm not sure if Carl ever speculated about, I haven't read all of his books, but that's a rather unexpected thing that's happened in the last few years is the discovery of comets passing through our solar system that fairly clearly come from outside the solar system. In other words, they were formed around another star elsewhere in the galaxy, and it's in the news at the moment because of 3I Atlas, which is the third of these objects that just came through this year. So none of these have come very close to the Earth so far, and they've all been flashing through so fast that there was no feasible way to design, for example, and build a spacecraft to go and visit them. You know, they were gone by the time you had a chance to think about that. But one can imagine some point in the future where one comes in on a slow enough orbit, or we detect it with one of the new telescopes that's large enough that we see it when it's out beyond the orbit of Neptune, and maybe we have 3 or 4 years to mount an expedition to go and see it. So you have any thoughts about what we might learn if we could go and actually pick up pieces, not of just material in our own solar system from other objects, but material that's come from another solar system completely? And what do you think Carl might have thought of that?
Well, I think he'd be excited about that because getting a larger sample size of information is always a good thing. We only have the one sample of life on Earth here to extrapolate to all of those planets that are far away from us. So, I mean, I'd be excited about that. I think he would be too. He was very excited about lots of topics in planetary astronomy, not just the search for alien life. So don't mean to give the impression he was only ever doing that. But I would also be fascinated with that and seeing what sorts of materials come from comets around other stars.
All right. I'd like to thank you all again so much for coming and celebrating with us. If we could get one last round of applause for Gillis.
Thank you.
Just as a quick reminder, despite the very heavy cloud coverage tonight, Fuertes Observatory, of course, will be open until midnight. So feel free to stop by. I'm sure Gillis will be there if you have any other questions.
I'll probably take this turtleneck off, though. It'll be too warm.
Perhaps. So I would once again like to stress, we are so glad you all came here today, and I hope you guys have a wonderful night.